Let us now study our next parameter, electric potential, denoted by capital V. इलेक्ट्रिक पोटेंशियल को हम लोग कैपिटल V सिंबल से डिनोट करते हैं. इलेक्ट्रिक पोटेंशियल समझने के लिए पहले हमें पैरामीटर हाइट समझना है. ये हमारा अर्थ जिसका मास कैपिटल M है, एक ऑब्जेक्ट अर्थ के ऊपर है जिसका मास स्मॉल m है, उसको हम लोग हाइट h ऊपर लेके जा रहे हैं. कैसे लेके जाएंगे? सपोज दिस इज ऑब्जेक्ट ऑफ मास स्मॉल m ऑन अर्थ सरफेस. अर्थ के सरफेस पे ऑब्जेक्ट को रखा है. इसको मुझे ताकत लगा के, फोर्स लगा के अगेंस्ट ग्रेविटेशनल फोर्स ऑफ अर्थ ऊपर लेके जाना है. आई हैव टू डू वर्क अगेंस्ट द ग्रेविटेशनल फोर्स ऑफ अर्थ ऑन दिस ऑब्जेक्ट. दिस वर्क is stored as potential energy in this mass small m. ये ऑब्जेक्ट जब यहां था तो उस पे मैंने वर्क किया और उसका एनर्जी बढ़ाया, और एनर्जी बढ़ा के वर्क कर करके मैं उसको ऊपर हाइट h लेके गया. उसके कारण इस ऑब्जेक्ट के पास अब पोटेंशियल एनर्जी आ गया. पोटेंशियल एनर्जी mgh, फॉर्मूला सबको पता ही है. इसके पास कितना पोटेंशियल एनर्जी है? mgh. वो क्यों आया? वर्क करने की वजह से. Because of the work done on the object against the gravitational force, this object has potential energy. अब उसके कारण ही हम लोग एक पैरामीटर हाइट डिफाइन किया है. मोर द हाइट मोर द पोटेंशियल एनर्जी. अगर इस ऑब्जेक्ट को मैंने इस हाइट पे रखा तो इसका पोटेंशियल एनर्जी कम है, इस हाइट पे रखा तो पोटेंशियल एनर्जी ज्यादा है, उस हाइट पे रखा तो और पोटेंशियल एनर्जी ज्यादा है. मोर द हाइट मोर द पोटेंशियल एनर्जी. सो I will have to do more and more work to take it to more and more height. Hence, height can be thought of as work done per unit mass. Height can be thought of as work done per unit mass. More the work done, more the height reached. Height can be thought of as work done per unit mass. ये कोई फॉर्मूला नहीं है, ये सिर्फ एक एनालॉजी हम लोग ले रहे हैं हाइट एंड पोटेंशियल का. More the work done, more the height. Height can be thought of as work done per unit mass. वैसे ही इलेक्ट्रिक पोटेंशियल अगर हमारे पास अर्थ और मास के बजाय, सपोजिंगली ये हमारा इधर अर्थ था और ये मास स्मॉल एम है जिसको हम लोग ऊपर लेके जा रहे हैं. ये अर्थ है और ये मास स्मॉल एम है जिसको हम लोग ऊपर लेके जा रहे हैं. दिस इज सोर्स मास, दिस इज टेस्ट मास. वैसे ही यहां पे हमारे पास क्या होगा? सोर्स चार्ज. इलेक्ट्रोस्टैटिक्स में हमारे पास होगा सोर्स चार्ज. सोर्स चार्ज लेट अस से कैपिटल क्यू. कैपिटल क्यू सोर्स चार्ज. उससे मैं टेस्ट चार्ज स्मॉल क्यू को एक पॉइंट से दूसरे पॉइंट लेके जा रहा है, तो भी मुझे वर्क करना पड़ेगा. जैसे अर्थ के ग्रेविटेशनल फोर्स के अगेंस्ट मैंने इस मास m को ऊपर लेके गया, वैसे ही इलेक्ट्रोस्टैटिक्स में सोर्स चार्ज के इलेक्ट्रिक फील्ड के खिलाफ मैं उस टेस्ट चार्ज को दूसरे पॉइंट पे लेके गया. I will have to still do work. That is what is the definition of electric potential. Electric potential at a point is defined as work done per unit test charge to take from infinity to a point where electric potential is to be found. जैसे हमारे पास हाइट था वर्क डन पर यूनिट मास, वैसे ही है इलेक्ट्रिक पोटेंशियल. हाइट इज अ पैरामीटर हियर. Similarly, electric potential is a parameter here. Height is work done per unit mass. Electric potential is work done per unit test charge. अब ये फॉर्मूला तो हमें समझ गया उस एनालॉजी से. Work done is nothing but energy. Work done is nothing but energy. तो इसलिए मैंने W को क्या लिख दिया? कैपिटल Q, कैपिटल U. कैपिटल U अपॉन Q, ये भी हमारा इलेक्ट्रिक पोटेंशियल का डेफिनेशन हो गया. अब इलेक्ट्रिक पोटेंशियल का फॉर्मूला हम लोग ने पिछले सेक्शन में देखा है, दैट इज K Q1 Q2 अपॉन R. K Q1 Q2 अपॉन R. यहां पे Q1 इज सोर्स चार्ज कैपिटल Q, Q2 इज टेस्ट चार्ज स्मॉल q. तो इसलिए K Q1 Q2 अपॉन R बिकम्स K कैपिटल Q स्मॉल q अपॉन R. और ये जो डिनोमिनेटर में Q है वो एज इट इज रखा है. डिनोमिनेटर का Q आई हैव केप्ट एज इट इज. स्मॉल q cancels out. What we are left with is K capital Q by R. This is another formula for electric potential in terms of source charge. K Q by R. Electric potential की दो फॉर्मूला में याद रखने हैं. One is this one, electric potential work upon test charge. दूसरा फॉर्मूला K Q by R, where Q is source charge. Capital Q denotes source charge, small q denotes test charge. Electric potential V is W by Q is equal to KQ by R. What is R in this case? R is the distance from source charge to point where we have to find electric potential. Again, I will repeat it. Small r is the distance from source charge to point where we have to find electric potential. So this is the formula for electric potential at a point. Now, electric potential difference between two points. जैसे हमारे पास यहाँ पे हाइट एक पॉइंट लिया मैंने A, यहाँ पे हाइट है HA, दूसरा पॉइंट B लिया B, वहां पे हाइट है HB. तो हाइट डिफरेंस क्या होगा? HB माइनस HA या फिर HA माइनस HB. सिमिलरली अगर मेरे पास एक पॉइंट यहाँ पे है, लेट अस से A, दूसरा पॉइंट है B. Yes. So when I move the test charge from one point A to another point B, what is the potential difference? जैसे वहां पे height पैरामीटर है, यहाँ पे potential पैरामीटर है. VA is the potential at point A, VB is the potential at point B. So VA minus VB becomes UA minus UB upon Q, because V is U by Q. V is U by Q. So VA will be UA by Q. VB will be UB by Q. VA minus VB will be UA by Q minus UB by Q. Therefore, VA minus VB will be UA minus UB by Q. So this is another formula for electric potential difference between 2 points. Also, we know from the previous section, electric potential energy is a scalar quantity. So, electric potential will also be a scalar quantity. In scalar quantities, as I said in the previous section, we have to take utmost care of the sign of the charge. यहाँ पे Q1, Q2, कैपिटल Q जो भी लेना है, वहां पे हम लोग को साइन लेना है उसका. अगर यहाँ पे कैपिटल Q सोर्स चार्ज जो है वो पॉजिटिव है, तो फिर वहां पे प्लस साइन आएगा, और सोर्स चार्ज अगर नेगेटिव है तो माइनस साइन आएगा, और पोटेंशियल भी उस पॉइंट का नेगेटिव रहेगा. टेस्ट चार्ज इज टेकन एज ऑलवेज पॉजिटिव आर्बिट्रेरली हम लोग टेस्ट चार्ज को ऑलवेज यूनिट पॉजिटिव टेस्ट चार्ज मानते हैं. So electric potential and electric potential energy both are scalar quantities, and we have to take care of the sign of the charge. Electric dipole. Di means two, pole means charges. Two equal and opposite charges separated by a distance constitute a dipole. Thus, electric dipole means two equal and opposite charges separated by a finite distance. The distance we denote by 2L. Dipole moment. Dipole moment is denoted by symbol small p. It is a vector quantity. It is defined as magnitude of charge into distance between the two charges. Thus, magnitude of charge is Q and distance between two charges is 2L. Thus, dipole moment is magnitude of charge into distance between two charges. Here P vector denotes electric dipole moment. Q is magnitude of charge. 2L is distance between plus Q and minus Q. Direction of dipole moment is taken from minus Q to plus Q in physics and plus Q to minus Q in chemistry. Again I repeat, direction of dipole moment is from minus Q to plus Q in physics and plus Q to minus Q in chemistry. Electric potential due to dipole. Suppose we have a dipole with charge minus Q and plus Q. The potential at a point P at a distance small r from the midpoint of the dipole is given by the formula electric potential V equals Kp cos theta upon r square, where K is Coulomb constant, P is dipole moment, theta is angle Pm plus Q. Theta is angle Pm plus Q. Electric field due to dipole. Electric field due to dipole is given by Kp upon r cube root of 3 cos square theta plus 1. Again the setup is same. A dipole minus Q and plus Q separated by distance 2L. M is the midpoint of the dipole. P is the point at which electric field is to be calculated. Theta is angle Pm plus Q. R is distance Pm. Minus Q to midpoint is L and plus Q to midpoint is also L, because the total distance between minus Q and plus Q is 2L. For axial or end-on position, angle theta is 0. That means for axial or end-on position, the point P will lie on the axis of the dipole. For equatorial or broadside on position, angle theta is 90. That means point P will lie on the perpendicular bisector of axis of dipole. Point P will lie on the perpendicular bisector of axis of dipole. That is equatorial or broadside on position. Potential due to electric dipole. Consider a dipole minus q plus q separated by a distance 12. M is the midpoint of the dipole. We have to find the electric potential at point P at a distance r from the midpoint of the dipole. The potential is a scalar quantity. Therefore, total potential at point P equals sum of potential due to positive charge plus potential due to negative charge. That is what we are writing here. Total potential at point P equals potential due to positive charge plus potential due to negative charge. Potential is a scalar quantity. Hence, we have to take sign of the charge in this equation. Potential due to positive charge, we will consider positive sign for the charge. Potential due to negative charge, we will consider negative sign for the charge. Distance from P to plus Q, we have marked as R1. Distance from P to minus Q, we have marked here as R2. What is the relation between R1 and R and R2 and R? From geometry, we can construct a perpendicular from plus Q to this line segment PM. To the line PM, we will draw a perpendicular from plus Q, meeting at this point here. If we consider the trigonometry, we can calculate this distance to be L cos theta. Similarly, on the line segment PM, we will again draw perpendicular from minus Q, meeting at this point. From minus Q, we will draw a perpendicular to the line segment PM. Again, from trigonometry, we can mark this line segment as L cos theta. From geometry, we can almost assume that this distance R1 equals R plus L cos theta. This distance R1 equals R plus L cos theta. That is what I have written here. R1 is R plus L cos theta. Similarly, this distance R2 can be thought of as R minus this distance L cos theta. R2 equals R minus L cos theta. That is what I am writing here. R2 equals R minus L cos theta. Both these relations come by approximation. We will substitute the value of R1 and R2 in this equation. So, in this equation for potential, the total potential at point P equals potential due to positive charge plus potential due to negative charge. So, potential due to positive charge is KQ by R1, this distance. Potential due to negative charge, KQ by R2, this distance. KQ by R2. Where we will take negative sign because this is potential due to negative charge. R1 we have proved is R plus L cos theta. R2 we have proved is R minus L cos theta in this relation. So we will substitute the value of R1 and R2. We will get this equation for potential KQ by R plus L cos theta minus KQ by R minus L cos theta. How do we get the minus sign here? We will move this minus sign from bracket, plus and minus becomes minus. Taking KQ common in the next step, potential becomes KQ bracket open 1 upon R plus L cos theta minus 1 upon R minus L cos theta. Then cross multiplying, we get this equation. Cancelling off R plus R and minus R cancels off. Minus L cos theta and minus L cos theta becomes minus 2L cos theta. We're taking the magnitude. We get potential V is equal to KQ upon R square into 2L cos theta. Combining this Q into 2L into one term, because charge into distance between two charges is nothing but dipole moment. Hence, we have put this in a box. Charge into distance is dipole moment. So, dipole moment is denoted by the symbol P. Dipole moment is denoted by the symbol P. So, this equation becomes Kp cos theta upon r square minus L square cos theta, which we have written here. Kp cos theta upon r square minus L square cos square theta. Now, if this distance r is much greater than L, if this distance r is much greater than L, then L can be neglected. That means r square minus L square cos square theta becomes r square. R square minus L square cos square theta becomes r square because L is negligible. For r much greater than L, L can be neglected. L can be neglected means this L square cos square theta term can be neglected. Therefore, the potential becomes Kp cos theta upon r square because L square cos square theta is neglected. So the final answer for the potential at point P due to dipole becomes Kp cos theta upon r square, where P is electric dipole moment, K is Coulomb's constant, R is distance, Pm this distance, Pm, R is this distance, Pm, and theta is angle Pm plus Q, angle Pm plus Q, that is theta. Electric field due to dipole. Consider this dipole. This is positive charge plus Q, this is negative charge minus Q. Let us first understand the axial and equatorial position of a dipole. This distance is L, this distance is L. So the total distance is 2L. The line passing through the two charges, the line passing through the centers of two charges is called the axis of the dipole. So this line is called as the axis of the dipole. Any point on the axis of the dipole will be called as axial position. Suppose I consider this point. This point lies on the axis of the dipole. So this point is axial position. And I consider the midpoint of the dipole M. And if I draw a line perpendicular to it, this line. So in this line, if I consider any point on the perpendicular bisector of the dipole, then this point will be called as equatorial position. Let us say this is the perpendicular bisector of the dipole. So this point, any point on the perpendicular bisector will be called as equatorial point because it is passing through the perpendicular bisector of the dipole. So that is about axial and equatorial position of the dipole. The same thing we are seeing in this figure. Let us first consider the electric field at axial position. This is a dipole plus Q minus Q separated by distance 2L. M is the midpoint of the dipole. So this distance is L and this distance is also L. Consider a point P on the axis of the dipole. Consider a point P on the axis of the dipole. Electric field due to positive charge points away from positive charge. So hence I have shown E plus in the left direction because electric field due to positive charge plus Q will be pointing away. Away means in this case left direction. Similarly, electric field due to negative charge minus Q will point towards the negative charge. Hence I have shown E minus towards the negative charge. So electric field due to positive charges away in left direction. Electric field due to negative charges towards in right direction. So the net electric field will be electric field due to positive charge minus electric field due to negative charge because the two electric fields are pointing in opposite directions. Now the formula for electric field KQ by R square. So KQ by R square, let us think about the distance between midpoint of dipole and point P. It is denoted by distance R. Similarly, the distance between plus Q and midpoint is denoted by L. The distance between minus Q and midpoint is denoted by L again. So, the distance between plus Q and point P, the distance between plus Q and point P will be R minus L. So, this distance, the distance between plus Q and point P will be this distance, which is R minus L. Hence, this distance is R minus L the whole square. So, electric field due to positive charge will come out to be KQ upon R minus L the whole square. Similarly, electric field due to negative charge. So, for that, let us consider the distance from minus Q to point P, where we have to find electric field. So, that distance is this total distance, the distance between plus Q, no, the total distance between P and minus Q is given by R plus L. The distance between P and minus Q is given by R plus L. Hence, the distance P minus Q will be R plus L the whole square. R plus L the whole square will be the electric field term in this case. Electric field due to negative charge, KQ by R square. KQ by R plus L the whole square. Substituting the values of electric field due to positive charge and negative charge in the below equation, we get this new equation. After that, taking KQ common, we get electric field net is KQ bracket open 1 upon R plus L the whole square minus 1 upon R minus L the whole square. Cross multiplying, we get this equation. R minus L the whole square minus R plus L the whole square upon R plus L into R minus L the whole square. Now, A plus B into A minus B becomes A square minus B square. A plus B into A minus B becomes A square minus B square. Similarly, R plus L into R minus L becomes R square minus L square. And this square term remains out of the bracket in the power. Expanding the term R minus L the whole square and R plus L the whole square, we get R square plus L square minus 2RL minus R square minus L square minus 2RL. Everything cancels off except minus 4RL. Minus 2RL becomes minus 4RL. Minus 4RL, its magnitude will be plus 4RL. Hence, the net electric field will be KQ into 4RL upon R square minus L square the whole square. So, this comes out to be 2K Q into 2L upon R square minus L square the whole square. Why did I write 4 as 2 into 2? So that this term Q into 2L can be replaced by dipole moment. If you remember, dipole moment was charge into distance. Hence, I will replace this term charge into distance in the next step by dipole moment P. Hence, we have taken this two common outside. So, the electric field becomes electric field at axial positions 2 kpr upon R square minus L square the whole square, which for R much greater than L. If R is much greater than L, then L can be neglected. So, neglecting L in this equation, R square raised to 2 becomes R raised to 4, and R raised to 4 in the denominator cancels out to give R raised to 3 in denominator. Hence, the net electric field at axial position becomes 2 kp upon R cube in approximate form for R much greater than L. This is the electric field for axial position for a dipole. Coming to the electric field at equatorial position due to dipole. As we have seen before in our demonstration, we had two charges, plus Q and minus Q. And equatorial position was the point on the perpendicular bisector of the dipole. So let us consider this as point P, which is on the perpendicular bisector of the dipole. The electric field due to positive charge points away from positive charge, which is what I have shown by E plus. Similarly, electric field at point P due to negative charge will be towards the negative charge, which I have shown by E minus. Let us call this angle as theta. In that case, this will be alternate angle theta. If this is alternate angle theta, then by symmetry, this angle also comes out to be theta. This can be proved easily for perpendicular bisector position. If this angle is theta, then this is alternate angle theta, which are equal. Similarly, if this angle is theta, this angle will also come out to be theta. So, taking the components of electric field due to positive charge, the component with theta will be E cos theta. Similarly, the component of electric field due to negative charge along with theta will be again E cos theta. So, E cos theta due to positive charge, E cos theta due to negative charge. So, the net electric field in the right direction becomes 2E cos theta. What about the sign components? The electric field sign component will be in upward direction for positive charge. For negative charge, electric field will be in the sign component of electric field will be in the downward direction. The sin theta component of positive charge and the sin theta component of negative charge cancel out. So that is why I have not shown it in figure. Coming to the net electric field due to dipole, we are now seeing it is 2E cos theta. For cos theta's value, what we do is we redraw this triangle on the right side. So I am redrawing this triangle on the right side. This angle is theta. The opposite side is r and the adjacent side is L. By Pythagoras theorem, the hypotenuse will come out to be square root of r square plus L square. So the cos theta, by definition, becomes adjacent side upon hypotenuse. So L upon r square plus L square's root. So this is the value of cos theta. This value of cos theta will substitute in the equation for net electric field. So electric field net becomes 2E into, in place of cos theta, I have substituted this value. So cos theta becomes L upon root of r square plus L square. So the net electric field becomes 2kq upon r square plus L square. How do we get this? Electric field is kq by r square. Electric field is kq by r square. For this point, what is the distance from charge to this point? So this distance is r square plus L square's root. Hence, we'll write electric field is kq by root of r square plus L square the whole square. kq by r square. So kq upon r square plus L square. And cos theta remains as it is. The value of cos theta is L upon root of r square plus L square. Now, writing the square root of r square plus L square as r square plus L square raised to half by mathematics. So what do we get? Net electric field is 2kq L upon r square plus L square, bracket open, r square plus L square raised to half. Combining the powers of these two terms, what do we get? In the denominator, r square plus L square raised to 3 by 2. The numerator remains as it is. We have combined this q into 2L together so that we can replace it in the next step by dipole moment P. Q into 2L can be replaced by dipole moment P. That is what we will do in the next step. So electric field at equatorial position becomes Kp upon r square plus L square raised to 3 by 2 by substituting P in place of Q into 2L. After that, for r much greater than L, again we will neglect L. If I neglect L, r square raised to 3 by 2 becomes r cube. R square raised to 3 by 2. 2 cancels. And what we are left with in denominator is r cube. So electric field at equatorial position becomes Kp upon r cube for r much greater than L. To summarize, the electric field at axial position for r much greater than L is 2 Kp upon r cube. The electric field at equatorial position for r much greater than L is Kp by r cube. So these are the two derivations which we should remember for our exams. Moreover, if the point P does not lie on either axial position or equatorial position, it can lie anywhere. For that also we will derive the expression for electric field at any general point in our next